First, the continuity equation. Second is the conservation of momentum. Pressure tensor is diagonal now just because this is with the FOM. And then there is the conservation of energy, which becomes temperature plus 2/3 divergence of U theta equals 0. So this is the continuity equation. This is called Euler's equation. And there's no heat transfer. So the temperature equation does not describe heat conduction. We can simplify it a little bit to review its physical significance. Now, this quantity appears very often. This is called the material derivative. ddt plus u gradient of something. And sometimes we just write this as df dt. This is the rate of change of this quantity f if you follow the motion along the average velocity. That is, if you move right along with the fluid on a streamline, that describes the time rate of change. In order to reduce this equation, let us consider the following equation. The time the material of rho theta to the minus 3/2 is computed. This is the d rho dt. It's a linear operator, so we use d rho dt. From theta to the minus 3/2 minus 3/2 theta to the minus 5/2 d theta dt. And this is equal to this equation can be this is the rho dt. Let me factor the theta to the minus 3/2 minus 3/2 rho over theta d theta dt times theta to the minus 3/2. But this combination, I can see, is equal to 0 by the equation up there. By hydrodynamic equation. So this is equal to 0. And then that equation is equivalent to d dt of rho theta to the 3/2 is equal to 0. And this says that the quantity rho even my 3/2 is equal to constant along a streamline. Now, it so happens that rho temperature to 3/2 equal to constant is a condition for an adiabatic transformation in thermodynamics. This implies adiabatic transformations along streamline, that is no heat exchange. Which is not surprising because we showed that there is no heat vector. So that you travel along the streamline, the gas does not exchange heat with the surrounding. It's adiabatic. I guess, do you know that this is the constant? Do you know that this is a adiabatic condition? You can derive it very fast. I'll derive it here very fast. What you do is you take the du, which is minus pdv plus pdx. Adiabatic means it's equal to 0 for adiabatic. And so you have this. And you notice for that gas u is equal to 3/2 nkt, and pv is equal to nkt. When you plug this in, you get this condition. So, so that's n over v times t to the minus 3/2 is constant for an adiabatic transformation. You can derive very simply and now negative elasticity. So the equation for non-viscous hydrodynamics is very simple. First, this continuity equation, and this Euler's equation, which is really Newton's equation. Because the left side is just the acceleration, and the right side is just the, if you bring a delta to the other side, it's just the force. And then you have the condition of the no heat exchange. But even so, there are some very interesting applications of this non-viscous hydrodynamics. So I'd like to discuss some applications just to show that they're useful. So let's plot that. Sound wave. In a gas, how do you jitter the sound wave? The sound wave is a correlated motion. A correlated oscillation of the density. And it is possible only if the mean free path is much shorter than the wavelength. So you can have local thermal looping. So consider small deviations. From the equilibrium of Maxwell-Boltzmann. So du, d rho, d theta, these are considered first order small. Here's the concept of order again. That is, you ignore second order small quantity. We just keep the first order small quantity. That is, the product of these two will be neglected. And then you take d dt, you have d rho dt plus rho gradient u is equal to 0. So let me put in one more step. The original equation is delta of rho u. But this is equal to 0. But this is equal to d rho dt plus rho divergence of u plus u dot gradient rho. Now this is neglected because the second order is small, because u is small and the gradient is small. So you neglect it, therefore you will only leave with this equation. Therefore the continuity equation reduce to d rho dt plus rho. I really use it. And then you have the Euler equation, du dt plus gradient of p equals 0. Suppose there is no external force. Let's consider f equals 0. Now you take ddt of this equation. You take gradient of this equation. From the first operation, you get d2 rho dt squared plus rho times gradient of du dt plus d rho dt times divergence of u. But this is second order small, so you neglect this. From the second, you get rho ddt divergence of u plus Laplacian of t. Now you add these two, you subtract this equation. You subtract those equations, and you get d rho dt squared minus Laplacian of p. Now p is the pressure. The pressure is a function of rho. That's called the equation of state. So when I take the derivatives of p, I can convert those into derivatives with rho. So I will write Laplacian of p is equal to the divergence of the gradient of p is equal to the divergence of the gradient of rho times dp d rho, because p becomes rho. And so this is equal to Laplacian of rho times dp d rho plus second order term, which I neglect. Then we have a wave equation. Minus 1 over c squared times Laplacian of rho is equal to 0. Where 1 over c squared is equal to dp d rho. And in doing this, I must keep the entropy constant because there's no heat exchange. So this is a thermodynamic coefficient that you can measure experimentally. And c is the velocity of sound. This is sound. The wave equation describes sound, and c is the velocity of sound. And the velocity of sound can be expressed in terms of a thermodynamic coefficient, which is the compressibility. That is, one usually defines the compressibility as a derivative between p and rho. Kappa of S is defined as 1 over rho times dp d rho at constant entropy. This is called the adiabatic compressibility. And so in sound wave, the sound, when the air oscillates, Chinese sound wave, the compressibility is adiabatic because there is not enough time to exchange heat. Because in this non-viscous case, there's no heat exchange. And it's interesting as a historical note that Newton was the first to try to compute the sound velocity by such derivations. But he made a mistake. He used the isothermal compressibility. He thought that the temperature is constant. So he found it disagrees with experimental Violet. And he was very disappointed, but you have to use the adiabatic. And that condition came from our third equation. So that's a nice application. Consider the second application, which is also interesting. I'd like to emphasize this point that if the mean free path is very long, then there will be no sound wave. Sound wave is an organized oscillation of the gas, and that organization comes about only because locally they have time to reach equilibrium. In a Knudsen gas, in the collision regime, there will be no sound wave. And because we are in the zeroth order approximation in non-viscous thermodynamics, there is no damping on this now. The sound will go on forever, it doesn't damp. When we go to the next approximation, we will find damping from viscosity. This is a potential flow. Suppose we neglected the force over there. Suppose this is an external force, and it is of the form of a potential, a conservative force. And let us consider du dt to 0. Consider the static case. With a static. This is a vector identity. Which I'll just write down, but you can verify. U dot gradient U can be written in a very nice way as identical as 1/2 the gradient of U squared minus U cross the curl of U. You can prove this by writing it component by component and verify that it's true. Just the X, Y, Z components, just work it out. If I use this identity, the equation I want to discuss is d dt U plus U dot gradient U plus 1 over rho gradient of P is equal to minus 3.5%. Now I apply the x identity to the second term. I'll get 1/2 but du dt is 0 because U is constant. Then I get 1/2 Laplacian of U squared minus U cross U plus 1 over rho gradient P is equal to minus 1 over m gradient P. this is equal to gradient of P over rho minus P gradient of 1 over rho, and is equal to gradient of P over rho plus P over rho squared delta rho. So this whole thing can be written as the gradient of u squared over 2 plus P over rho plus phi over m is equal to u cross curl u minus P over rho squared gradient rho. So I convert it into this equation. Now from here on, there are two cases I can specialize. The case one is when the density is uniform, that is delta, the gradient rho is 0. So a uniform fluid. Uniform density. E-rotational flow. Which means that gradient of rho is equal to 0 and curl u is equal to 0. In which case I get gradient of u squared over 2 plus P over rho plus phi over m is equal to 0. And this is Bernoulli's equation. This is very, I think you've seen it before. You can use it. For example, let's use it as an example. Consider gravity. Consider a liquid under gravity. If this is phi, is equal to mgh, where h is the height measured from the surface of the Earth. And then suppose I consider a tank. I consider point A here and a point B here. U is equal to 0. Okay. And bigger U has a certain velocity going down. Now I want to, and this height is h. What is the velocity u? You have done it before in your elementary course. But now let's derive it very simply from it. It just comes from this. Because this whole thing is a constant, I just equate this quantity at A to that at B. So I get 1/2 u squared at this point should be equal to minus 1 from rho, the pressure at B minus the pressure at A, plus G HA minus HB. And this can be neglected. If this tank is not so high that the atmospheric pressure at 2 points can be very different. So if I neglect this, I just get U is equal to square root of 2GH, which I think you know this answer. Just for fun, if you plug in, say suppose H is 1 foot. Then you will find a U. I will use 8 feet per second, which is reasonable. Is it reasonable? You take a tan of 1 foot, the water comes out at about 8 feet per second. And also this tells you that if this constant, especially if the pressure goes down, then U has to go up, which is the principle by which the airplane wing gets its lift. Let's go to the second example. You see, when we considered the Maxwell-Boltzmann distribution, you recall, we neglected the external force. I think this supplies the answer to that. Suppose you put a gas in an external potential, say like under gravity. How would its density change with height? We can use this equation. We can use that equation. So case 2. Uniform temperature. Irrotational flow. So that gradient theta is equal to 0. Curl U is equal to 0. But ideal gas P is equal to rho theta over m. This ideal gas equation of state in terms of theta and rho. And therefore the gradient P is theta over m times gradient of rho, theta being a constant. And that theta is where KT is. So let's get U squared over 2 plus phi over m is equal to minus theta m rho delta rho, which is equal to minus theta over m gradient of log rho. Or gradient U squared over 2 plus phi m plus theta over m log rho is equal to 0. Doesn't mean that this thing is a constant. Right, U squared over 2 plus phi over m plus theta over m log rho is a constant, say C0. So I solve for rho, I'll get log rho is equal to m over theta times C0 minus U squared over 2 minus phi over m. Or rho is equal to some constant, some exponential minus m U squared over 2k, theta is kc, over kt, over 2kt. This is Maxwell-Boltzmann, minus phi over theta, minus theta over kt. And if I put it under gravity, the density of a column of gas will equal to rho 0 times e to the minus m u squared over 2 kT minus mgh over kT. And if there's no motion in the gas, you just have this, you just have the density decreasing exponentially with height, and that's a well-known result. So if u is equal to 0 and rho is just equal to rho 0 e to the minus m c h over kT. Now you might wonder, do the numbers make any sense? Suppose I've got hydrogen atoms. How do I calculate it? It's important to be able to plug in some numbers, you know. And it's important to be able to do it in your head. So you have to remember a few numbers, then you can calculate some numbers. So let us just have a computer for a gas of hydrogen. Without running to the handbook of physics and look up things. So consider a column of hydrogen. G is 9.81 times 10 to the 2 centimeter per second. That you should know. So suppose let's take 80 is 1 centimeter. And what's mgh over kT? So let's say kT is 300 degrees Kelvin. What is mgh over kT? For hydrogen. Well, I would do it this way. I would multiply both this by mc squared over kT, that's dimensionless now, times gh over c squared. These are dimensionless quantities now. This I can compute. This is equal to 9.81 times 10 to the 2 times 1 centimeter divided by 3 times 10 to the 10 squared. And I get roughly 10 to the minus 18. And this is equal to hydrogen. mc squared of hydrogen is 2 GeV. Right? This is twice the proton mass, 2 GeV. What is an electron volt? It's 2 times 10 to the 9 electron volt. A good thing to remember is that room temperature is 1/30th of an electron volt. And so this gives you six times 10 to the minus 8. And then rho is equal to rho 0 times e to the minus 6 times 10 to the minus 8 times h in centimeters. Now we take 1 centimeter, that's very small. So we take 1 centimeter, detect how hard it changes. How far you have to go before it changes appreciably? For the density to go to 1 over e of this value, h has to be equal to 1 over 60 times 10 to the minus 8, or 1/6 times 10 to the 8 centimeters. And that is about 100 kilometers. Well, atmospheric height, isn't that all right? And so that's, those are examples for this non-viscous hydrodynamics. But of course it has its limitations, because We are expanding in the mean free path, and this is in the limit when we ignore the mean free path. It's very small. So there is no dissipation at all. So we assume that the distribution function is locally in Maxwell-Boltzmann. And we find that in this approximation, it lasts forever. The thing just flows. There's no viscosity, it doesn't decay. But this flow pattern, non-viscous flow, will last forever. That is, the lifetime will be infinite. But of course, you know that there's viscosity. And that comes in the second order, in the first order. So we'll make a first order approximation to get viscous hydrodynamics. So I'm going to introduce this subject now, and maybe we can finish it today, but I'll just introduce the subject. So first order approximation. Now you put the F0, the local Maxwell plus a correction G. And you see that G is much less than F0. Now you have to solve for G. You have to plug this into the Boltzmann equation and solve for G. And this is a very hard problem. To this order, you really have to struggle with the collision interval. And that's what Maxwell did. He solved it. We are not going to go through all that labor here, but we'll make a shortcut. We'll treat the problem making a linear approximation. After all, this enables the system to approach the Maxwell-Boltzmann distribution. So we'll just say that EFD collision is probably equal to minus F minus the Maxwell-Boltzmann distribution divided by the collision time tau. This makes the Boltzmann distribution linear. And it's a very useful approximation, and it's qualitatively correct. But tau is what the relaxation time. It's a time over which the system approaches equilibrium. And it should be of the order of the collision time. Which, as you recall, is the mean free path divided by the average velocity, which is about equal to 10 to the minus 11 seconds for average condition. And now the Boltzmann equation reduces to something very simple. It says dEt plus P over M gradient plus F equal to V F 0 plus G is equal to minus G over tau. And of course, on this side, you can neglect it. It's the first order. Once you negate, there's nothing to solve. G is given by this. So it's very, very simple. So that to first order, the correction to the derivative G is given by minus tau on ddt with P over M factorial plus F factorial with the P of the local Maxwell-Boltzmann distribution. So P and X. And we have solved the Boltzmann equation. That's it. Now the job remains to calculate the heat flux vector in the pressure tensor from this, from the F given by F plus G, and plug it back into the hydrodynamic equation. Then you get viscous hydrodynamics. In particular, the momentum conservation equation, which is the most important, which we obtain as Euler's equation, now will involve viscosity. It will become the Navier-Stokes equation. The computation is, even though everything is explicit, the computation is pretty messy. So I'm not going to go to on a blackboard here, but you all fall asleep. It's in the book anyway. But I want you to know what we're doing. So let me just give some preliminary results. Now you compute it. First you get Q. Straightforward enough, but it's a long calculation. Finally you get Q is minus a constant times the gradient of theta. And this is just the heat flux vector, well-known heat flux vector. What is the gradient of the temperature? And K if we do all the calculations, it's given by m to the fifth power times this tau, 6 times the interval d3u, u to the fourth, m with 2 theta, u squared minus 5 halves times f0. If we do the integral, it just comes with 5 halves tau theta n. And of course, this is the coefficient of thermal conductivity. So you see that we have obtained this thermodynamic coefficient in terms of the collision time tau, which is the microscopic parameter here. If you really solve the Boltzmann equation analytically, you will find something similar to this. The only thing changes is 5 halves. The rest is just such dimensional. So if you improve the calculation, all you say is change the 5 halves to something else. So this approximation is really very convenient. Now the pressure tensor. That's very interesting. We have to devote some time to discuss that. But if you compute it just straightforwardly, plug it into the equation straightforward, you'll find the following. The pressure tensor was defined, as you remember, as a correlation between velocity and average over the product of two velocities, right? It's velocity correlation. And you apply our formula, you'll find that Pij is equal to, first the first one, del Ijp, that's the zeroth order approximation. The first one will give you minus 2 mu over m times lambda Ij minus m over 3 delta Ij Divergence of u. This is lambda ij. I think when I defined it before, I left out a prefactor. It's m over 2 times dui dxj plus duj dxi. Symmetric tensor. And with mu, is the integral of 2 m5 tau m5 over theta times the integral d3u ux squared y squared f0 integral tau and theta. It's the same dimension as the coefficient of thermal conductivity, and this is viscosity. Now, as I say, that this looks a little complicated. We're going to discuss the physical significance of these terms later. And this is the first order correction, and also viscosity. But you know, there's something interesting. That the thermal conductivity, coefficient of thermal conductivity and the viscosity, they are of the same dimension. So the ratio is a pure number. First, you notice that the viscosity is independent of the temperature. No, don't say this. It's independent of. Now we'll come to that. But you will notice that k over mu. This is going to 5 halves. And this 5 halves we interpret to be, just to make it general for, general to all gases, it's 5/3 times CV. The CV is 3 halves for a monatomic gas. But we replace it in general. So we seem to have a law that K over CV for mu is 5/3. It's constant, independent of anything. So we can measure this. Take gases and measure K, mu, and CV and see if it's right. And we'll make a plot. Temperature. We'll plot here K over CV mu, and here's 5/3. The measured value is it's not bad. It's nice. You get points like this. From minus 200 degrees Kelvin, 200 degrees centigrade to 200. These are different gases. So it's not perfect, but it's not bad. Now you substitute these into the hydrodynamic equation. First, the continuity equation, of course, is not effective. It's exact always. So you get d rho dt plus gradient of rho u equals 0, as always. The second one, you get d dt in material derivative plus u dot is equal to F over M, the external force, minus 1 over rho times the gradient. It used to be just the pressure. Now it's more generous, the pressure, minus mu over 3 divergence of u plus mu over rho of Laplacian of u. This is called a Navier-Stokes equation. And then the temperature equation gives you ddt plus u dot gradient theta is equal to minus 1 over CB, which is 3 half, times divergence of u times theta plus K over rho CB times Laplacian of theta. Now if in the last equation you put u equal to 0, that is no flow, put u equal to 0. If u is equal to 0, then this equation just becomes d theta dt is equal to some constant k over rho CB times Laplacian of theta. And this is a diffusion equation. But the heat, the temperature changes propagates by diffusion in the heat exchange. So we have this. We have this. And these are the equations of first order viscous hydrodynamics. Of these equations, I would say that the most significant is Navier-Stokes equation. Now we take a poll among physicists and engineers as to what is the most important equation there is of all time. You get different answers, right? I guess you will get. I think Maxwell's equation will be pretty high on the list. But I think Navier-Stokes equation might even be more popular among engineers because it applies to the weather. It describes the ocean. It describes everything. So that's a very important equation, and we will develop a little bit of time to discuss the significance of these terms next time.